What I'm going to show you now is the physical connection between what's happening on a PV plot and what happens in life. So to demonstrate this, I've got a plastic syringe here. Now it's a plastic syringe, which means that it's not very thermally insulated. So given a little bit of time, it will come to thermal equilibrium with the surrounding environment. At the bottom of the syringe, I've got some sensors. So I've got a pressure sensor and a temperature sensor. And this is hooked up to the computer so that you'll be able to see what's happening to the pressure and the temperature as I take this gas through a process. So to read off the volume, we read the volume from the side of the syringe here. So we're starting with 60 milliliters of air, and I'm going to compress it down to 20 milliliters. Now the syringe is just filled with air. So air is predominantly made up of nitrogen and some oxygen. So it's predominantly diatomic molecules. Okay, so what I'm going to do is I'll compress it really quickly. So because I'm doing it quickly, it means that there's no time for the heat to flow. And so ideally, this is an adiabatic process. Okay, so there's the adiabatic compression, and now I'm holding it down and allowing it to come to thermal equilibrium with the surrounding environment. So you can see that the temperature is leveling off, and eventually it gets back to the initial temperature. Now that it's back at the initial temperature, I'm going to slowly expand the gas. Because I'm doing this slowly, I'm allowing it to come to thermal equilibrium with the surroundings, and so this is a isothermal expansion, or the best I can manage with this equipment. So now it's returned to its initial state. Now if we were to plot this on a PV plot, it would look like this. What we're going to do now is work out the change in internal energy, the heat added and the work done during each of those steps in this thermal process. So here's our PV plot. We're going to calculate the change in internal energy, the heat added and the work done on each of these paths and for the cycle. But before we do, let's just calculate the pressure, volume at each of the points around our cycle. So first of all, we know that inside the syringe is air, and air is predominantly nitrogen molecules and oxygen molecules. So these are diatomic molecules, and this was done in my office at room temperature. So this tells us that F is equal to 5. So we'll be making use of this. Now if we assume, as we've done to generate this PV plot, that point A has a volume, so VA is equal to 60 milliliters, and that the pressure A is equal to 1 atmosphere. Now, point B, that's at 20 milliliters, and point C is also 20 milliliters. So this is 20 milliliters. This one's also 20 milliliters. But let's go and calculate the pressures for this now. So the pressure at B, to get this, we'll need to make use of the fact that this is an adiabatic process. And for adiabatic processes, we've got PV to the gamma is constant. Now gamma is equal to Cp over Cv, which is equal to F plus 2 on 2 R over F onto R. We can cancel out the R on 2, and we have F plus 2 on F. So in this case, this is equal to 5 plus 2 on 5, so this is equal to 7 on 5, or 1.4. So using our adiabatic equation, we've got that PAVA to the 1.4 is equal to PBVB to the 1.4. And so PB is equal to PA times VA on VB to the 1.4. So this is equal to 1 atmosphere times VA, which is 60 milliliters, over VB, which is 20 milliliters. So the milliliters cancel out to the 1.4. And so this gives us 4.66 atmospheres. Now, just looking back at our plot, you can see it didn't quite get up to 4.66 atmospheres, but it got fairly close. When we're doing experiments like this on the desktop, we're not going to be able to get the absolute highest pressure because the temperature starts to drop off very quickly, and our equipment has a certain sampling rate, so it can't necessarily sample fast enough to get the absolute highest pressure or temperature. Okay, so this pressure, PB, is equal to 4.66 atmospheres. So now we're going to use this to try and calculate what's going on along path A and B. It's adiabatic, so by definition we know that Q is equal to 0. So now what we want to do is calculate the change in internal energy and the work done. To do that, we can make use of our first law of thermodynamics. The change in internal energy is equal to Q plus W. So we can just calculate either the internal energy or the W, whichever's easiest. W is possible. We could integrate the work done is equal to minus the integral of P dV, and we can get an expression for P in terms of V using this equation here, but it does end up as quite a complicated integral. So in this case, it's not actually the easiest way to do it. So let's use our equation that the change in internal energy is equal to F over 2 times nR delta T. And so this is equal to F over 2 nR TB minus TA. And now what we'll need to do is use our other favorite equation, the ideal gas law, PV is equal to nRT, to write T is equal to PV on nR. So we can write this as F over 2 nR times TB, which is PB VB over nR, minus PA VA over nR. These nR's all cancel, and we end up with F over 2 PBVB minus PAVA. And we've got values for all these things, so now we can substitute in. We've got 5 over 2. Now I'll put my conversion factors for the units outside the brackets because they apply to both these terms, so that'll just save me some writing. So this is 4.66 atmospheres times 20 milliliters minus 1 atmosphere times 60 milliliters. Now my conversion factors to convert from atmospheres to pascals times 1.01 times 10 to the 5, and then to convert from milliliters to meters cubed, it's times 10 to the minus 6. So it's 10 to the minus 3 to get to liters, and then times 10 to the minus 3 again to get to meters cubed. And so solving this, I end up with 8.38 joules as my change in internal energy. So the change in internal energy is equal to 8.38 joules, and then through the first law of thermodynamics, because Q is 0, I can see that my work done is also 8.38 joules, and as I expect, that's a positive number because this is a compression. Okay, so now we're going to look at B to C. We'll want to start by calculating, well, what is the pressure at C? So in order to do that, let's consider the path C to A. We know that this is isothermal. Sorry about my spelling. I'll write this again. Isothermal. And for an isothermal process, we've got the equation PV is equal to constant. So this tells us that PAVA is equal to PCVC, i.e. the P times V here is the same as P times V here. And so this tells me that PC is equal to PA times VA on VC. So PA, that was 1 atmosphere, times VA, which is 60 milliliters, over PC, which is 20 milliliters. So this ends up as 3. And so this is equal to 3 atmospheres. So PC is equal to 3 atmospheres. Now you can see in reality, we had around about 2.7 atmospheres, so fairly close, but not exact. Part of the reason for that was actually that though I tried my best to compress it down to 20 milliliters, it was quite hard to keep it there, so the volume actually ended up being just slightly larger than the 20 milliliters. Okay, so what we're trying to do now is calculate what happens along path B to C. We can see along this path that the volume isn't changing, so we know that the work done along this path is equal to 0. So now our first law of thermodynamics tells us that we can either calculate the change in internal energy or Q. Now to do the change in internal energy, we do exactly the same process this way. So let's just mix it up a bit and calculate Q this time. Now in this case, this is a constant volume process. So this is NCV times delta T. So this is equal to N times F over 2R times delta T. So that's TC minus TB, which is equal to F over 2 times NR. Now TC, just using this equation again, we've got PCVC over NR minus PBVB over NR. NR's cancel, and we end up with F over 2 PCVC minus PBVB. So let's calculate this. We've got 5 over 2 times, now once again I'll put my conversion factors outside the brackets. So PC, that's 3 atmospheres times 20 milliliters minus PB, which is 4.66 atmospheres times 20 milliliters times 1.01 times 10 to the 5 times 10 to the minus 6 to get from milliliters into meters cubed. So solving this on the calculator, I end up with minus 8.38 joules. So this tells me that Q is equal to 8.38 joules, minus 8.38 joules, and the change in internal energy is also equal to minus 8.38 joules. Okay, so we've just got this one path here left to calculate. This is isothermal, so we know that the change in internal energy is equal to 0. So now we need to calculate Q and W. We don't know how to calculate Q, so we're going to have to calculate W. So to calculate W here, we know that the work done is equal to minus the integral of P dV, and we'll be going from volume C to volume A. So what we'll need to do here is substitute in for P in terms of V. So we can use our ideal gas law up here and write, well, P is equal to nRT on V. So substituting that in, we've got our work is equal to from VC to VA, and we've got nRT on V dV. So we've got minus nRT, and then we're doing the integral of 1 on V. When we integrate 1 on X, or 1 on V in this case, we end up with the natural log. So this is equal to minus nRT times the natural log of V, VC, VA, which is equal to minus. Now, because we don't know the T, what I'm going to do is I'm going to substitute in PV on NR here. Now, we can choose any spot along here because they're all isothermal, all at the same temperature. So let's just go with point A at the end. So we've got PAVA over NR instead of T. And then we've got here, this is log VA minus log VC. Okay, so this NR now cancels that NR, and we might end up with minus PAVA log. Now, I don't know if you remember this, but with your log rules, if we're subtracting 2 logs, we can write them as a fraction inside. You don't have to do that. But this is the expression that we end up with, which is now something that we can evaluate. So PA, that's 1 atmosphere, so minus 1.01 times 10 to the 5 pascals. And VA, that is equal to 60 milliliters, so 60 times 10 to the minus 10 to minus 6, because it's milliliters. And then times log. Now, VA, that's 60 milliliters, and VC, that's 20 milliliters. The milliliters will cancel out there. So inside here, we end up with 3. So we can now solve that, and we end up with minus 6.66 joules. So we've got that our work done is equal to minus 6.66 joules. It's good to see that it's negative because it's an expansion, so that's what we expect. And so Q then, from our first law, has to be equal to 6.66 joules. Okay, so we've calculated it for each of these paths now. Let's have a look at the cycle. The change in internal energy, you can see we've got 8.38 getting up to B, getting down minus 8.38 and then 0. So around the cycle it's 0. For the heat added, we've got 0, and then we've got minus 8.38 joules, and then we've got plus 6.66 joules, and so this gives us minus 1.68 joules. And for the work done, we've got 8.38 joules done, compressing it to B, none done coming down to here, and then minus 6.66 joules. So that's equal to 1.68 joules. So around the cycle, the heat added and the work done need to cancel each other out so that we end up with the same, with no change in the total internal energy.